So today I'm going to present a paper from SCA 2008, which is related to facial animation. The main idea is that they introduce a concept of Postpaste to actually generate fine scale details like this. So they want to animate a face with motion capture, this sparse mode, but they still want to generate the fine scale details of this animation. So they propose another method to do that.
Did you present this paper before?
No, not in the seminar at least. Yeah, no. So in summary, this paper, well, they deal with the real-time animation of highly detailed facial expressions. So they propose a kind of hybrid approach. It's not purely computational, it's not data-driven either. It's a mix of them. So some of the main contributions is that they do a multi-scale decomposition of the facial geometry. That means that first they address the large-scale motions by using a computational method, which is a fast linear thin shell model. So this actually is somehow from the markers, try to get the large scale, and then using a data-driven approach, then introduce the fine scale details. So the fine scale details are based on the Postpaste deformation techniques. So it's similar with the paper that actually Yomo had a few times. So I will go in more detail later. So this allows for separate the editing on large and fine deformations. So you can just set up the large scale using the markers or by moving them. But then if you are not happy with actually the fine scale details, you can also go there and refine. So they present also some applications for this. So first is the real-time motion capture. Then how to actually transfer details of these fine scale details like wrinkles and skin bulge to another model. And finally, how to interactively editing this. So in this case, it means that if you have just a model without fine scale, you can just apply this method and create them in an artist way. So in the overview, first we want to deal with the large scale deformation. So the starting is a high res pose, rest pose face mesh. So they use more or less a 1 million triangle space like this. Then this is driven by a set of handle positions, like the marker of the motion capture. And then using a linear thin shell model, which is actually somehow like similar to Laplacian editing or RBF editing, then they generate the large scale deformations. Then in order to do the fine scale deformation, they first need some example pose set. These example poses are...
So how do they achieve large scale deformation using the small number of handle boxes?
So
with the detail later?
yes, so basically, I will explain. This is just the overview.
Okay.
But basically, these are constraints, and then somehow this is transfer. This displacement vector is somehow smoothly transferred to the other areas, while maintaining the original shape. So for the fine scale, we have this kind of example set. These example set are P-poses, which are done by few high-resolution meshes, which have this fine details. And then also, these fine details are somehow extracted from this. So first, this rest pose with no details is matched to this pose. And then actually the displacement between this large scale and the fine details is stored in some kind of tangent space displacements. Finally, in order to associate this displacement to actually a pose, they create a mesh from the handles, and then in this mesh they actually encode how the surface stretch. So then they learn a system how actually the stretch of the skin generates this 5-detail scale, and then when the system is learned, then they can just apply this to generate. So finally, the final result is just the summation of both, and then they can achieve this kind of results. So now for the details in this large-scale deformation. So the main idea is that given a set of constraints, which are the handle positions, they want to minimize the stretch and bending of the surface. So somehow it keeps the original stretch and bending of the rest pose. So this is similar to solving actually the Euler-Lagrange equations. So first we have to consider this is what we want to solve, is the displacement of a vertex from its rest pose. And then what we have as input information is the constraint, which are actually the displacements given by the user or the motion capture. Then in this corresponds to this. So actually this is the stretching energy of a mesh, and then the bending of the mesh. So this is in the continuous case. So if we somehow discretize and then try to solve this, it corresponds to this Euler-Lagrange equation. So this discretization corresponds to the Laplace-Beltrami operators. So this can be solved by actually solving this linear system, which corresponds to the rest pose Laplacian weights of the constraint vertex and the free vertex. And then we want to solve the displacement from the non-constraints. So since all this data just depends on the rest pose, we can pre-compute this in this case. And then the solution just comes from a new displacement of the constraint handles. Then we can just obtain the new displacements by simply multiplication. So for the fine scale deformation, the wrinkled skin bulges is what it's referred to fine details. However, these details actually are not really linear in nature. They appear, each very similar phases may have very different skin details depending on many factors that cannot really be parameterized. So the key observation that they do is that these fine details are associated with a specific pose. If I raise my brow, then the skin will wrinkle in a specific way. And then if I just do the same pose again, the wrinkles should be the same. So they associate between these fine scale details and a specific face pose. And then the variation between them is somehow smooth. So if I have a little less brow raise, then the details somehow get interpolated. So these are the main observations. And finally, that all of these details come from somehow the skin strain, how they stretch and bend. So to do this, the main idea is how can we define a pose space? So what makes a pose? Is it like the positions of the vertex at a specific point, or is something else? So in this case, because the face can move, they want something that is rotation invariant, and it's somehow related to the skin strain. Skin strain. Not, that would be creepy, but yeah. So to do this, they create a feature vector. So we cannot use the position of the handle vertex because it depends on really the, if you translate or rotate, then everything changes. So that's not good. So what they do is first they generate a mesh from the handle vertex, like this. And then they want to encode the stretch of this mesh by using this. So they can, for each edge, F, it will be F1, F2. Then they can compute the stretching of this like this. So first they compute the length at the current frame, And then they just rest it by the rest pose and then just normalize it. So in this case, at the rest pose, the value is just 0. And then the more it stretches, it gets bigger. And then if it's stretched or compressed, then also they can compute the sign. So if you look like this at the somehow the rest pose, then actually the stretch is very simple. But then when somehow it becomes like this. So you can see a little bit how these Fi values change depending on the different stretches. So putting all these stretches in a vector, this is what makes define one pose. So now the question is, now we define a pose, we can somehow parameterize the pose into a pose space. Then how can we transfer these details into that pose? So we have an example, we have a pose, and then actually we have a displacement from the rest pose. So the question is actually, how can we learn a mapping between the pose and the displacement? So what they do is actually compute an RBF, train an RBF functions on this. So I think more or less everybody is familiar with the RBF. So it's just interpolation. So first we need to estimate these weights, and then once the weights are learned, then we can get for any new pose, we can estimate the displacement. But this has a big problem. Actually, this feature vector encodes the face globally. So for example, if I have the eyes closed and I smile, it's a different pose than actually just smiling. But actually these wrinkles are local. So this means that if we want to just use the postpaste deformation, we will need a lot of examples and it will be a very heavy RBF. So what they come up is some weighting this postpaste deformation. So in order to do this, they somehow redefine this feature distance in a per vertex way. So the main idea is like this. Now, for each vertex, actually, we will compute some distance to the vertex, an example. So this would be this, we sum all over the stretch, and then this would be the stretch of the H and the Jth example. And then this is a kind of weighting parameter based on the distance. So it seems a little bit complicated, but basically the result is like this. So this alpha bi is weighted. For example, if a vertex is on the edge, this weight will be 1. If you actually, as the vertex gets away from the edge, then the weight somehow diminish. So basically the effect of a specific stretch will only affect to the vertex that are close to this area. So then this distance is somehow summated from all over the vertex. So that means that the contribution of this edge will only affect somehow this vertex, not this one here. So in this setup here, actually the summation is all over the edges. So yeah, so actually this is the new equation. So in this case, the difference is now actually we have, it's a little bit more complex. So now the weights are not general. There is not a weight set for the whole face, but there is a weight set for actually every single vertex. So this makes the system like vertex times more complex. So one way they can actually reduce this is actually we can observe that actually the influence of a specific edge, it affects just very few amount of vertex. So we can just somehow get the 16 edges that influence that vertex, and then just use this as the RBF system.
So how do you select the 16 edges?
So as you can see here, the 16 is arbitrary. They just, so it's based on these weights. So for example, this vertex here, you can compute this is actually the weights for this edge. But here there will be another edge. So this weight.
They compute like what if they were to be measured to have edges?
Yeah, more or less. So basically they, in a first preprocessing step, they just compute kind of this alpha weight for every edge. We could like, we consider this vertex here. So this edge will have very strong weight. This one also very strong. But this one will be very low. So they just pick the 16 heaviest weight. So they just say that the 16, there is no reason for that. They just say it's reduced enough to actually.
So our old edges possibly pick the strongest 16.
Yes. So actually it would be more or less is the closest ones.
That means you compute the weight for all the edges of the mesh.
Yeah.
Take 16 out of.
Yeah. So basically they just do the pre-processing. Then they just find for each vertex which are the 16 best edges, and then they just keep that. But they don't study actually if they can just, for example, it would be reasonable to assume that maybe this vertex on the edge actually just depends on one edge, and then maybe this one just on 3 or 4. But they don't study anything about this. So they just basically say that they want to reduce the system. Yes, so that is. So these are more or less the results that they get from this. So on the left you can see just the large scale, and then here is the result with the deformations. Yeah, so you can see here this local space somehow generates good deformation, even when it's not symmetric. So they say that because of their feature vector, you can actually, this feature vector is invariant to rotations and everything. Is actually at the rest pose, the feature vector is just 0, 0, 0, 0. So if you actually somehow match both, if you have two faces, one with fine scale details and another one with just normal large scale, just a normal model, then if you actually somehow match these two faces with a good correspondence, then you can actually transfer all these details almost in a very straightforward way. So this is, so first we need to find the dense correspondence. So this is first by manually selecting some sparse correspondence. Then we can estimate the rigid rotation, the rigid transformation, including scale, rotation, and translation. And then after this, they apply their large scale deformation to actually match both surfaces. And in this case, they can project the vertex onto the other meshes to actually generate one-to-one correspondence between one surface and the other. Then the transfer can be done automatically by actually estimating, transferring the weights of the RBF directly to the other one. Since sometimes the vertex doesn't have like a perfect matching, then they just do some kind of linear interpolation using the barycentric coordinates of the surface. So in this case, here is the idea. Like this model has nice fine scale details, but this one they just scan it, so they couldn't actually spend many time. They just scan the rest pose. So as you can see on the left is just the basic motion capture without the scale. And these are the results from the skin wrinkles from actually the guy. So they say they, well, more examples with other meshes. So in terms of performance, they say that actually their method is really friendly for parallelization. Basically, all they need is matrix multiplications. And also you can pre-compute many things. So all of this, like the system matrix for the large scale deformation, the RVF weights, and actually also the edge weights can be stored already on the GPU. And then only the new posts and the new displacement have to be somehow updated every time. So in their examples, they use they somehow sell it as an advantage. I think actually it's also a limitation. They actually can work very fast with very high detail meshes, but at the same time, their method cannot be applied to normal resolution for animation. So for example, like for the skin models, they really need very high deformation, so they cannot work with displacement maps or anything. So yeah, it's a little bit. But in any case, they can actually achieve this 30 frames per second with very high resolution meshes. So they did some tests with blend shapes and like the normal PSD, and then actually they show two ways of actually computing the weights for the weighted post-paste deformation. One is just a normal interpolation, and then the second one is a least square fitting. But for this case, there is not much difference. So here are the results. The main thing that I don't really understand is actually they say they use local blend shapes, which is just a normal way of doing blend shapes, but they don't actually specify how they compute these blend shapes. They don't say if it's a fax or actually they somehow compute it from some examples. And they don't also mention how many blend shapes they actually use. So I think this evaluation is a bit, what they mention is, which is reasonable, is that actually, as you can see in this here, it's like, for example, here some markers are just disappearing. So because the blend shape is somehow fitting, then it doesn't necessarily exactly fit to the marker positions. Wherever the large scale deformation, which is somehow like driven by the markers, then they always achieve this. But I think in general the results are quite good anyway. So actually I don't know exactly what's here. But here is the main difference between the weighted space or the post-space deformation. So they use actually the same number of examples. So as you can see, because this is kind of a global picture, you can see that even though this area is not stretching, because somehow it's an interpolation between two examples, there is some stretching appearing in this area. So they somehow prove the weight space can somehow behave locally. Yeah. So this is just the introduction of that paper. So if you have some questions, if not, then just finish. Okay, thank you.